So continental rifts, have been intensely investigated for clues to processes that initiate continental breakup and passive margin development. Nevertheless, a topic that I've really been interested in is that to date, considerable speculation remains regarding the fundamental geodynamic processes that initiate and sustain the evolution of magma deficient or what we call magma poor rifts. And this has just been largely due to the lack of data from these rift systems. The picture in the background is a Landsat image of the Okavango alluvial fan. Let me see if I can get my pointer here. Of the Okavango alluvial fan, which formed as a result of new tectonic activity associated with incipient rifting. My work on rifting actually started with the investigation of the Okavango rift zone. So studies suggest that breaking up cold, thick continental lithosphere is really hard to do. And numerical models, typified here by the Bock 2004-2006 models suggest that the forces that are required to extend thick lithosphere is greater than geologically available, such as presented here in the top figure. However, addition of a weakening agent, such as melts or volatiles, or perhaps as a dike intrusion as shown in this model, can soften the lithosphere, reducing the forces that are required for extension. So this is really the current paradigm that is supported by observations from mostly magma-rich rift systems. So nevertheless, the magma-poor rifts really challenge this paradigm due to lack of associative volcanism at the surface. And so our understanding of these magma-poor rifts remains fragmentary. Over the last 5 to 10 years, several large-scale experiments such as the PRIDE and the segment experiments have been conducted that allow us to begin filling in the knowledge gaps and allow us to address the fundamental questions related to the formation of magma-poor rifts, such as what are the softening or weakening mechanisms responsible for the formation of these magma-poor rifts? Is it pre-existing structures, or is it melt at depth that are yet to breach the surface? So to answer this question, we look at the East African Rift System, which is an ideal location to address these questions because it exhibits both magma-rich and magma-poor segments. And the eastern branch here shown here is very magma-rich, whereas the western branch and the southwestern branches are magma-poor. And within the western branch, we have just isolated magmatic centers at the tip of the rift basins or systems. So numerical models by Koptev et al. 2014 to explain the coeval formation of magma-poor and magma-rich segments within one geodynamic setting have suggested that a rising mantle plume is deflected by the cratonic keel of the Tanzanian craton, preferentially channeling magma to the east, resulting in the magma-rich eastern branch, while leaving the western branch magma-poor. In this presentation, I want to focus on two sites, the Okavango Rift Zone and the Malawi Rift Zone. Both represent magma-poor rifts, but they are at different stages of their development. So let's go to the Okavango Rift Zone then. The ORLZ is developing within the northeast trending Proterozoic belt sandwiched between the Congo Craton and the Kalahari Craton. Although the rift is about 150 kilometers wide, although the zone of the formation for the rift is about 150 kilometers wide, what we see here is that intense faulting is occurring only within a 60-kilometer wide region and in the southeast. And in this region, we see that the rift faults are strongly aligned with Proterozoic structures or with the basement fabrics as shown here in this aeromagnetic image. The Curie point depth estimates from inversion of the magnetic data as shown here suggest that we do have elevated heat flow within the rift zone, again, limited to within the 60-kilometer wide zone of intense faulting. When we look at Moho depth estimated from gravity data, we also see that there's thinning of the crust, which we see is also seen in passive side, not passive, active source seismic data across the Okavango Rift Zone also shows an elevated Moho of about 4 to 6 kilometers. So, but to really answer the question whether there's melt present or not, we have to look at the upper mantle structures. And to this, we turn to passive seismic data. And so I'm presenting several data sets here from Yu et al. 2017 and White Gaynor et al. In 2020, and also S-wave velocity models from Fidel et al. In, I think it's 2020. So the studies by Yu et al. Image a low velocity anomaly of approximately 1%, negative 1% beneath the Okavango reef zone, and they relate it to the conventional melting from thinning of the lithosphere and estimated temperature anomaly of about 100 degrees C. Whereas White Gaynor et al. 2020 that imaged the same low velocity anomaly within the Okavango reef zone, similar within Okavango reef zone, related actually to a much broader zone of low velocity anomalies associated with the Damarian belt. And instead of relating this to a potential melt beneath the reef zone, they actually suggested that it may be the result of variability in the lithospheric thickness between the thinner lithosphere of the Damarian belt compared to the thicker lithosphere of the cratons. However, Fidel et al. In 2020 provided new 3D crustal and upper mantle shear wave velocity model of Botswana, and they document a middle cross shear wave low velocity anomaly beneath the Okavango reef zone as shown in these images. And I'm just going to point to two profiles, profile DD prime that goes across the reef zone, which is shown here, and we can clearly see a low velocity anomaly occurring at depth at a depth of about 135 kilometers. Incidentally, geochemistry data of volatiles from hot springs from this region of Botswana suggests potential mantle source. So taken together, the new data sets are suggesting thermal perturbation of the lithosphere and upper mantle beneath the Okavango reef zone. But the question is this low velocity anomaly or this thermal perturbation that we see due to the presence of melt? And we don't really have an answer for that yet because we don't have any melt models for Botswana. So let's move to the Malawi reef zone. In Malawi, the Malawi reef represents a more advanced stage of rifting than the Okavango reef zone. The rift is largely magma poor, except for the northern tip where volcanic centers of Rungo volcanic occur. Except for the North Basin, which we see right here and in the geologic map here, except for the North Basin, which is parallel to pre-existing structures, the central and southern segment of the rift cuts obliquely across Proterozoic basement terrains, really questioning the role of pre-existing structures on the localization of the rift. So let's see what the new data sets are showing us. So first we examine the crust to determine the extent to which the crust has been modified by magmatism, if at all. The mobile depth estimates from three studies, gravity studies from Ginger et al. 2019, and passive seismic studies from Accardo et al. 2020, and passive seismic again from the Sun et al. 2021 data. And it is remarkable how both three data sets agree in terms of the crustal thickness estimates or Moho depth estimates. As can be seen here along this south to north profile in the Yu et al. Study, and consistent with the gravity data, that we do not see any along axis thinning of the crust except in the North Basin close to the Rungo volcanic province. Okay, but what does the lithosphere tell us? In fact, the lithospheric images tell us a different picture. On the left is the lithospheric thickness derived from gravity data by Njinjo et al. 2019, and on the right is the lithospheric structure from Hopper et al. 2020. And here I've highlighted the lithosphere, the lithospheric estimates of boundary in yellow for clarity. And we can clearly see that along at the axis of the reef, so while we did not have any thinning of the crust, we do show thinning of the lithosphere beneath the reef system. In fact, along the entire axis of the reef, but more thinning in the North Basin as we consistent with the lithospheric thickness of the lithospheric structure. But what about the upper mantle structure? What is it telling us? So on the left, the figure on the left is a model of instantaneous lithospheric modulated convection of asthenosphere beneath the Malawi rift using aspect by Njinjo et al. 2019. And the LMC results from lateral variations in the asthenospheric upwelling beneath the Rungo volcanic province, the LMC results from lateral variations in lithospheric thickness that generate lateral temperature variations. So we see upwelling beneath thin lithosphere and downwelling within thick lithosphere. So the model shows that at 250 kilometers depth, upwelling is faster with a southward flow, towards the south. Upwelling is slower with a divergent horizontal flow. And the middle panel here shows the P-wave velocity models from Yu et al. 2020, and the bottom is melt fractions from Ginger et al. 2021, showing that we have a zone of low velocity anomaly, and this zone is also consistent with melt fractions of about 1 to 1.5%. So what did we learn then from the Malawi zone? We do have couple rifting in the north, where the thin crust and mantle lithosphere occur. We see strong alignment of rift basement structures, and we can suggest here that magma-assisted rifting is occurring due to the presence of the Rungwe volcanic province. However, the central and southern segments are different. We have thick crust but moderately thin lithosphere, this occurs where the rift cuts across basement structures. We see focused melt generated beneath the Rungwe volcanic province in regions of upwelling asthenosphere. And then we see southern flow of melt from the north may facilitate rifting in a magma poor segments to the south. So the key takeaways is that we see thinning of the crust pronounced where rift structures are strongly aligned with the Proterozoic structures. And we saw this both in the Malawi and the Okavango. We see that there's thermally perturbed lithosphere in the upper mantle in the upper 300 kilometers. But is this thermal perturbation really due to melt? We see that in Malawi, this melt is very focused and a very restricted region within the Rungwe volcanic province. And so far, although it's been suggested, we don't really have strong evidence. We don't have evidence for melt beneath the Okavango rift zone. There's no thermally perturbed mantle transition zone, which suggests the absence of any lower mantle influence on rifting. So if there are any mantle plumes, or if there are any kind of plume materials, they're actually sourced from a distant source, but not from directly beneath the rift zones. Moving forward, what I believe we need to do is we now have a lot of data sets. We need joint inversion schemes that integrate newly available geophysical data sets. We need some new numerical models that incorporate insight from geophysical imaging. We need to clarify the role of variability of pre-rift lithospheric heterogeneity, and we need more robust melt generation models that incorporate geochemistry data and reasonable estimates of mantle potential temperature. So before I open up for questions, I just wanted to introduce a new project that we have, and it's called the Dryer Project, or dry rifting in the Alberton Rhino Graben. And we hope to be able to address some of these outstanding questions, questions that remain. And our main goal is to elucidate the processes that drive magma pore rifting in continental rifting. So basically, we're looking at the Alberton Rhino Graben here. Here we have volcanic centers in the south, and the northern segment of the rift is magma poor. There's no magmatism at all. So what we want to see is how does the lithosphere and upper mantle structure change as we move from the magma-rich centers of the rift system to segments where there is no magmatism at all. So I want to thank the work that I've presented is my work that's been done from many students and postdocs, as many other scientists that have been focusing on looking at these magma pore rift systems. Thank you.
Thank you so much, Estella. That was a fascinating overview. If anybody has any questions, they can put them in the chat, or they could put their hands up as well. I can see that in the participant list if you put your hand up. In the interim, I have a question. In that last promo slide for this new experiment, I noticed there was MT on there. Is that the only MT that's being done in the area so far?
Yes, so far, yes.
Okay.
Yeah. So we're going to have, in fact, all geophysical techniques are going to be applied here. So it's like we're throwing a kitchen sink at the problem. So hopefully we're able to have some answers.
Excellent. Yeah, yes. I was thinking with the melt, it would seem that MT would be a great way to get started.
Yes, exactly. Yep.
Pretty easy to implement. I see Sasha's hand is up.
Mm-hmm.
Yeah, thanks for this nice talk. I would have one question on this inheritance. You mentioned this, if you don't have melts, then there might be inherited structures in crust and mantle that just promote localization. But what is your opinion? Where is this weakness residing? In crust, in the mantle? Is it thermal or is it mechanical? What do you think?
Yeah, that's a really interesting question, you know. And so I feel that to be able to answer that question, one of the things that we lacked from the Okavango and the Malawi experiments is empty data. In fact, we do have empty data over the Okavango. It's still being processed because the empty will really tell us whether or not it's melt. Since the numerical models are suggesting that there's just no way we can just extend rift without addition of melt. So these lithospheric weaknesses could extend all the way from the surface to the upper mantle. In the pride experiments, we do have an empty section that goes across Zambia, and we clearly see a Proterozoic shear zone that goes, we can clearly see it from the surface all the way, into the upper mantle. So.
Okay, thank you.
Yes.
There's just a question that's appeared in the chat from Leanne Strogi. Would you like to unmute and ask your question, Leanne?
Hi, thank you. This was a great talk. I really enjoyed it. It was a wonderful overview. I'm just wondering, maybe you just answered my question. If you know, in the Malawi, do the basement structures under the northern part extend through the crust, as your model would imply? Thank you.
What's your question again? If the
basement structures under the northern part of the Malawi.
Oh, the northern part.
Do you know whether they extend through the entire crust? So you're looking at the structures at the map level. I'm just wondering what you know about underlying structures.
I don't know if they extend through the crust. So one of the major faults there is the Livingston Fault. It's a pretty large fault with large displacements of more than maybe about 7 kilometers or so. And we don't have the fine detailed structures of the crust there. But I won't be surprised if they extend pretty, through the crust itself.
Thank you.
They do have empty. I think the segment project did acquire empty, but so far I've not seen any of the empty results published yet, which could also help us answer that question.